7 worlds dance in a delicate balance around a dim, crimson star, each a whisper of possibility in the vast silence of the cosmos. The TRAPPIST-1 system, a mere 39 light-years from Earth, beckons us to explore its mysteries, offering a glimpse into realms that could harbor life or challenge our understanding of what it means to be a planet. This faint star, barely larger than Jupiter, pulses with a quiet energy, its light bathing a family of rocky exoplanets in a glow that sparks dreams of distant shores. Could these worlds, nestled in the embrace of their ultra-cool dwarf star, hold the key to humanity's cosmic future? We embark on a journey to unravel the enigma of TRAPPIST-1, to peer through the lens of science and imagination, and to ponder whether these planets might one day call to us as a new home. This system is no ordinary stellar neighborhood. TRAPPIST-1, named after the transiting planets and planetesimal small telescope that first glimpsed its wonders, is a red dwarf star, an M-type beacon that burns cooler and longer than our sun. Its faint glow, just 0.05% of the sun's luminosity, belies its significance. Around it orbit 7 Earth-sized planets, each a potential stage for the drama of existence. These worlds, labeled TRAPPIST-1b through H, are locked in a cosmic waltz, their orbits so tightly knit that they complete revolutions in May days. The innermost planet, TRAPPIST-1b, races around its star in just 1.5 Earth days, while the outermost, TRAPPIST-1h, takes a leisurely 18.8 days. Their proximity to one another creates a gravitational symphony, a resonance that tugs and pulls, stabilizing their paths through the eons. This intricate dance is unlike anything in our solar system, where planets are spaced far apart, their orbits measured in months and years. The TRAPPIST-1 system lies in the constellation Aquarius, a faint speck invisible to the naked eye, with an apparent magnitude of 18.8, far beyond the human threshold of 6.5. Yet, its proximity to Earth, just 39 light-years, makes it tantalizingly close in cosmic terms. If we could stand on the surface of one of these planets, the sky would be a marvel. The star itself, TRAPPIST-1, would appear as a dull red orb, 10 times larger in the sky than the sun appears from Earth, casting a salmon-hued glow across alien landscapes. The other planets, so close in their orbits, might loom as bright disks, some larger than our moon, their surfaces reflecting the star's faint light. Imagine gazing upward to see a neighboring world, its craters or clouds faintly visible, a reminder of the crowded cosmic neighborhood. These planets are not mere curiosities. They are prime candidates in the search for life beyond Earth. 3 of them, TRAPPIST-1e, F, and G, reside within the star's habitable zone, that narrow band where temperatures might allow liquid water to pool on a planet's surface. This zone, often called the Goldilocks zone, is neither too hot nor too cold, a cosmic sweet spot where life as we know it could take root. TRAPPIST-1e, with an orbital period of 6.1 days, receives about the same stellar energy as Earth does from the Sun. TRAPPIST-1f, orbiting in 9.2 days, is slightly cooler, while TRAPPIST-1g, at 12.4 days, teeters on the edge of the habitable zone. Could these worlds harbor oceans, atmospheres, or even the faint chemical signatures of life? The possibility electrifies astronomers, who train their most advanced instruments on this distant system. The James Webb Space Telescope, a marvel of human ingenuity launched in 2021, has turned its golden honeycomb mirror toward TRAPPIST-1, seeking answers hidden in infrared light. Unlike visible light, which is drowned out by the star's glow, infrared radiation allows us to peer through the veil, capturing faint emissions from the planets themselves. These worlds are tidally locked, one face forever turned toward their star in eternal day, the other shrouded in perpetual night. This creates a stark contrast, one side scorched or bathed in warmth, the other frozen in darkness. The boundary between these extremes, the terminator line, could be a haven where temperatures are moderate, where liquid water might cling to rocky surfaces. The telescope's instruments, sensitive to the whispers of infrared, search for signs of water vapor, methane, or carbon dioxide, molecules that could hint at atmospheres or even biological processes. Yet, the path to discovery is fraught with challenges. TRAPPIST-1 is a flare star, prone to sudden bursts of radiation that bathe its planets in ultraviolet and X-ray torrents. These flares, far more intense than those from our Sun, could strip away atmospheres, leaving planets bare and lifeless. TRAPPIST-1b and C, the innermost planets, are likely scorched, their surfaces possibly molten or blanketed in thick, Venus-like atmospheres that trap heat in a runaway greenhouse effect. Even the planets in the habitable zone face this stellar wrath. A fragile atmosphere on TRAPPIST-1 might be eroded over millions of years, its gases torn away by relentless radiation. Without a protective magnetic field, common in planets orbiting so close to their stars, these worlds are vulnerable. Yet, there is hope. A dense atmosphere, rich in nitrogen or carbon dioxide, could shield the surface, preserving conditions for liquid water. Some models suggest these planets might even replenish their atmospheres through volcanic activity, outgassing molecules to replace those lost to space. The TRAPPIST-1 planets are remarkably similar in size to Earth, ranging from 0.77 to 1.13 times Earth's radius. Their masses, estimated through precise measurements of their gravitational tugs on one another, suggest they are rocky, with densities profiles akin to Earth or Mars. TRAPPIST-1d, for instance, has a mass about 0.3 times that of Earth, hinting at a thin atmosphere or perhaps none at all. TRAPPIST-1f, with a mass closer to Earth's, could be a water-rich world, its surface potentially covered in vast oceans or ice, depending on its temperature. These differences spark endless questions. Are these planets barren rocks, scorched and silent? Or do they host hidden ecosystems, perhaps microbial life thriving in subsurface oceans, shielded from the star's fury? The resonance of their orbits adds another layer of fascination. The planets are locked in a 3:2 orbital resonance, meaning for every 3 orbits of an outer planet, the next inner planet completes 2. This chain of resonances, unique in known exoplanetary systems, creates a gravitational harmony that stabilizes their orbits over billions of years. Imagine the sky from TRAPPIST-1f. The neighboring planets E and G would drift across the heavens, their positions predictable, the gravitational nudges felt as subtle tides. This resonance also aids astronomers, as the planets' frequent transits, passing in front of their star, allow repeated observations. Each transit dims the star's light by a fraction, revealing the planet's sizes and orbital paths. The Spitzer Space Telescope, before its retirement in 2020, and the Hubble Space Telescope have captured these transits, but the James Webb Space Telescope offers unprecedented precision, detecting subtle variations that could betray an atmosphere's presence. The star itself, TRAPPIST-1, is a relic of the early universe. At roughly 7.6 billion years old, it is older than our Sun, yet its low mass, about 8% of the Sun's, ensures it will burn for trillions of years. Red dwarfs like TRAPPIST-1 are the universe's most common stars, making up over 70% of the galaxy's stellar population. Their longevity and abundance make them prime targets in the search for life. If planets around red dwarfs can host life, the universe might be teeming with inhabited worlds. Yet, their faint luminosity requires planets to orbit perilously close to remain in the habitable zone, exposing them to intense radiation and tidal forces. TRAPPIST-1's habitable zone lies between 0.02 and 0.06 astronomical units, a fraction of the Earth-Sun distance. This proximity raises questions about tidal locking and its impact on climate. Could winds circulate heat from the day side to the night side, creating habitable niches? Or does the stark division between day and night render these worlds inhospitable? The James Webb Space Telescope's observations have already yielded tantalizing clues. In 2023, it detected possible signs of an atmosphere on TRAPPIST-1e, though the data remains inconclusive. The telescope's near-infrared spectrograph can analyze the light passing through a planet's atmosphere during a transit, revealing its chemical composition. A spectrum rich in water vapor or oxygen would be a groundbreaking discovery, though such signals are faint and require meticulous calibration. As Dr. Elena Martinez, an exoplanet researcher at MIT, notes, detecting an atmosphere is just the first step. We need to understand its stability, its chemistry, and whether it can sustain life over billions of years. The telescope's ability to observe in the mid-infrared, where planetary emissions are strongest, makes it uniquely suited to this task. Yet, the data is complex. A thick, cloudy atmosphere could mask signals, while a thin one might be too faint to detect. The TRAPPIST-1 system's compactness is both a blessing and a curse. The planet's close orbits mean they frequently transit their star, offering multiple opportunities for observation. However, their proximity to TRAPPIST-1 also means they are bathed in its flares, which can interfere with measurements. A single flare during a transit could mimic an atmospheric signal, leading to false positives. Astronomers must account for these outbursts, modeling the star's activity to separate its noise from the planet's whispers. The system's age adds another layer of complexity. Over 7.6 billion years, the planets have endured countless flares, potentially altering their surfaces and atmospheres. Some may have lost their water long ago, while others could retain it in subsurface reservoirs, much like Jupiter's moon Europa. Beyond the science, the TRAPPIST-1 system stays the imagination. Picture standing on the surface of TRAPPIST-1F, its sky aglow with the dim red light of its star. Neighboring planets hang like jewels in the heavens, their surfaces perhaps dappled with oceans or crusted with ice. The Terminator line, where day meets night, might host temperate regions where life could thrive. If intelligent beings inhabit these worlds, what might they see? Could they gaze back at Earth, a faint blue dot 39 light-years away, and wonder about life here? The possibility of advanced civilizations, perhaps using technology to harness their star's energy, is a distant dream, but one that fuels our curiosity. Some speculate that reflective structures, like vast solar arrays, could redirect light to the planet's dark sides, creating habitable zones where none would naturally exist. The broader context of exoplanet exploration adds depth to TRAPPIST-1's story. The universe is vast, with an estimated 200 billion stars in the Milky Way alone, each potentially hosting planets. Over 5,000 exoplanets have been confirmed, ranging from gas giants larger than Jupiter to rocky worlds smaller than Earth. Hot Jupiters, orbiting so close to their stars that their atmospheres boil, dominate early discoveries due to their ease of detection. Mini-Neptunes, with thick hydrogen-rich atmospheres, and super-Earths, more massive than our planet but smaller than ice giants, add to the diversity. The TRAPPIST-1 planets, all rocky and Earth-sized, are a rare find, offering a laboratory to study planetary formation and evolution. Their close orbits suggest they formed farther out and migrated inward, a process shaped by the star's protoplanetary disk billions of years ago. The search for exoplanets relies on ingenious methods. The transit method, used to discover the TRAPPIST-1 planets, measures the dip in starlight as a planet passes in front of its star. This technique reveals a planet's size and orbital period but not its mass or composition. The radial velocity method, which detects a star's wobble due to a planet's gravitational pull, complement transits by providing mass estimates. Together, these methods paint a picture of the TRAPPIST-1 system's architecture. Direct imaging, though rare, is another frontier. It requires planets to be large, young, and far from their stars, emitting enough infrared radiation to stand out against the stellar glare. The James Webb Space Telescope excels here, its coronagraph blocking starlight to reveal faint planetary signals. In 2024, it captured a direct image of a super-Jupiter in a distant system, a feat that underscores its power. The TRAPPIST-1 system's discovery in 2016, followed by the confirmation of all 7 planets in 2017, marked a milestone in exoplanet research. NASA's Kepler Space Telescope, though not involved in their discovery, set the stage by revealing thousands of exoplanets, showing that planets are as common as stars. Over 20% of Sun-like stars are thought to host Earth-sized planets in their habitable zones, a statistic that fuels optimism. The TRAPPIST-1 system, with 3 potentially habitable worlds, is a microcosm of this potential. Its planets' compositions remain uncertain, but models suggest they could range from water-rich ocean worlds to dry, rocky deserts. TRAPPIST-1H, the outermost planet, might be an icy world, its surface locked in a deep freeze, while TRAPPIST-1D could be a lightweight planet with a thin veil of gas. The dream of visiting TRAPPIST-1 is distant but not impossible. At current speeds, a spacecraft like Voyager 1 would take over 700,000 years to reach the system. Yet, innovative propulsion methods offer hope. Breakthrough Starshot, a proposed mission, envisions sending tiny, laser-propelled probes to the Alpha Centauri system, 4.3 light-years away. A similar approach could target TRAPPIST-1, though the journey would take decades even at 20% the speed of light. These probes, equipped with miniature cameras and sensors, could beam back images of the planet's surfaces, revealing whether they gleam with oceans or shimmer with ice. Such a mission, while technologically daunting, embodies humanity's drive to explore the unknown. The TRAPPIST-1 system also challenges our understanding of habitability. Red dwarfs, while abundant, are volatile hosts. Their phase and low luminosity create harsh conditions, yet their long lifespans offer billions of years for life to evolve. If TRAPPIST-1E, F, or G hosts life, it might differ vastly from Earth's. Microbes could thrive in subsurface oceans, shielded from radiation, or exotic biochemistries could emerge, adapted to low light and high ultraviolet. The planet's tidal locking might foster unique climates with eternal storms raging at the terminator or icy wastelands on the night side. These possibilities, while speculative, drive the scientific quest. The James Webb Space Telescope continues to probe these mysteries, its observations part of a broader effort to map the cosmos.